we can jump straight into our first talk, which is going to be, where is the testbed for my federated learning research? It was a work put together by Amandio and Janes, both, I believe, when they were in KAUST. Yeah, so the floor is yours.
Yes, hello everyone. I'm Amandio, research software engineer at KAUST, and I want to start by saying thank you to the Flower team for giving us the opportunity to talk about our work once again. We talked about an initial version of this current work. We had the chance to talk about this initial version of this current work in the Flower Summit of this year as a poster, and now we're here talking about it in the Flower Monthly, so we're very thankful to get the chance to share this with the Flower team. Flower community. Okay, so in this work, like Javier said, we're going to talk about our work, which we provocatively titled, Where is the Testbed for My Federated Learning Research? This is a collaboration between KAUST and University of Ljubljana with contributions from Janes, Boris, who is in the audience, Professor Velko, Professor Marco, and myself. Okay, getting right into it. The main challenges in evaluating federated learning algorithms are, one, the limited access to a diverse range of real devices, and two, the complexity of conducting experiments across these devices, all while measuring various performance metrics, such as inference accuracy, energy consumption, and time to convergence. However, due to these challenges, most FL evaluation results refrain from using the real devices where they aim to deploy their FL solutions, and instead they resort to running simulations. But if we never evaluate the algorithms on real devices, we're left wondering how they perform in real devices. What is the algorithm running time? What is the computational memory energy demand? And how do these change under real-world constraints, such as data, network, and device heterogeneity? To answer these questions, we decided to create a project with the goal of making FL evaluation over edge devices more accessible. And from this project came COLLEXT, the Collaborative Learning Experimentation Testbed. So COLLEXT offers a federation of 48 edge devices split between single-board computers and smartphones, allowing their users to reveal hidden hardware metrics, such as energy consumption and any potential hardware bottlenecks in the algorithms. But we didn't just want to offer the testbed. We also wanted to make it extremely easy to run FL research code on these devices. So we created a system that automatically gathers hardware metrics, helps you visualize them, and also takes care of orchestrating the experiments across the different devices. And all of this can be achieved by just adding 2 decorators to your Flower code. Okay, now we're going to take a look at the device composition in COLLEXT. So we have 48 total devices, but we wanted not just to have a large number of devices, we also wanted to have a diverse range of devices. And they needed to cover different architectures, performance capabilities, and hopefully also different vendors. For single-board computers, we have Orange Pi, which is that has an ARM architecture. We have Latte Panda, that is an x86 machine. We have 3 generations of NVIDIA Jetsons. So these are powerful single-board ARM devices that have CUDA-capable GPUs. And then on the smartphone side, we're currently only using Android devices, and we have 6 total different brands, including Xiaomi and Samsung, Google Pixel. And these smartphones, we again wanted to have a nice variety. So to pick low, mid, and high tier devices, we actually used a website called AI Benchmark that has rankings as to how different smartphones behave in benchmarks of AI inference. So based on these benchmarks, we picked a selection of devices so that we have low, high, and mid-tier devices. And in addition to these devices, we have a dedicated server that will act as a federated learning server. And this server also includes a GPU, which sometimes is required for certain types of federated learning, such as split learning. And we have a dedicated networking connecting all of the different single board computers and smartphones. And finally, we have a high frequency power meter, which we have used to measure the power consumption of smartphones directly. So just as a note, building and configuring the testbed required a lot of effort. So we actually documented our experiment experience, and so that we could assist further other research groups interested in creating their own testbed. And we'll give details. For more details, we'll share a link at the end of the presentation. But we hope this can be beneficial to other people. Okay, so now we saw the devices. Now we're going to walk through how you can actually interact with Collext as a user. Okay, so here's a quick overview of the interaction process. The green part shows the input that the user needs to provide, and the yellow part represents everything that is automated after that. So Collext will take care of this. Okay, so the first part, the first input that Collext needs is the FL code that you wish to run. And currently, Collext works with code written with the Flower framework. So we're targeting Flower specifically for now, but we try to make it general for other frameworks if we can. But to make it usable, we can just use default Flower code. We need to also add two decorators to it, one to the Flower client and another one to the strategy. But those are the only modifications you would need to your code. And then the other thing you need is to specify a configuration file that Collext, to tell Collext what you want to run and which devices you want to use. So you would specify the entry points for the client and the server, and also the devices that you want to use, the device type and the number of devices. And note also here that Collext, as part of the environment, Collext offers or exposes environment variables that you can use in the arguments, for example, the server address. So this is something that Collext will give you. And also, for example, if you need to know the number of clients, this is also something we provide as an environment variable that you can use in the configuration script for the entry point. Okay, so with those finished, the working directory can look very simple, just like this. We have the client code and the server code, which includes the strategy, the requirements txt file that lists all the dependencies, and the configuration file we just saw, where we specify the entry points and the devices we're going to use for the experiment. Okay, so that's really it from the user side. After that, Collext takes over. And at this point, all we need to do is from the directory of the code, invoke a Collext command, which is called Collext launch job, to launch the experiment as a job. And this experiment does a few things. One, it packages your code in the Docker container for the SPC side, for example. And then it deploys it to the node that you requested as part of the configuration file of Collext. And now the code is will start running on the devices. And because you decorated your Flower code with the Collext decorators, that decoration actually instruments the code so that we collect a bunch of different metrics. So we record hardware metrics and round statistics automatically just from the two decorators. Yeah, so we packaged the code, we deployed it, we're recording metrics, and printed while the experiment is running. You also get the job ID and the dashboard link that you can use, that you can access to monitor your experiment in real time. So here's what the dashboard looks like. In this image, you see two metrics that we're collecting. So one, power consumption, and another, GPU utilization. And you see we have some filters because with many rounds and many devices, interpreting the metrics can be quite challenging. So you can filter by specific rounds and specific lines that are being used in the experiment. And we also have this really neat feature where you can highlight the portions of the experiment that correspond to the different stages of NFL round. So fit here is shown in blue, and in red you see the eval stage of the round. So this really helps you see the spikes in power consumption as the devices start doing something. Yeah, and we hope that this dashboard, we found that this dashboard can be very useful to see and interpret the different metrics that we're collecting as part of Collext. Okay, but we don't just get access to the dashboard, you also get access to the raw metrics that you can use to do further processing if you want. So here we're seeing a CSV file of the hardware metrics that you get access to once you finish running the job. And to also provide quick insights, Collext automatically generates plots from these CSV files. So in this example, we're looking at one of the plots where we can see, so all of these lines correspond to one device. And we're seeing the training time for these devices, energy during the training time, and energy for the entire round. So even outside of the time that this specific device has been training, so considering the slowest device. And we see this split between the fit stage and the evaluation stage. Okay, so we saw roughly what Collext is, how you can interact with it. Now I'd like to discuss a few use cases that we see might be interesting for FL researchers to use Collext with. We're going to talk about a total of four. The first one is about comparing, revealing the trade-off really between accuracy and the resource usage required to achieve a certain accuracy. So in FL research, the final model accuracy is the most commonly reported metric, but the resources that were required to achieve the metric are rarely ever considered. So if we, for example, consider the energy required for the algorithm to reach its maximum accuracy, we might find that for a very small delta for a very small increase in validation accuracy, you might need to expend a lot of energy, which might raise some bells in your mind, and you start wondering if this small benefit of accuracy is actually worth all of this energy that you're expending to achieve it, especially if you're working on devices where energy is very limited or a very precious resource. So to play with this idea, we actually tested 3 federated learning algorithms on Collext with different model configurations and different value for different number of percentage of client participation per round. And our results do show that some algorithms consume significantly more energy for very small accuracy improvement. So as an example, we can look at the blue square at the top right and a very high pink triangle here. So these two settings, doesn't really matter what they are, but we see a benefit of about 2 to 3% accuracy increase. But if we consider the price that we're paying in terms of energy, we see that we're asking for 2 or 3% accuracy increase for 3 times more energy, which might not be worth it under certain circumstances. Yes, another valuable exploration or another possible use case for this is if we're evaluating these different algorithms in terms of the resources that they need not to reach their maximum validation accuracy, but to reach a target accuracy. And here we also see potentially expected but interesting trade-offs where if we look at these yellow shapes here, it's when we use the least amount of client participation per round. And this results in a higher time to accuracy, but because we're using few clients, actually the energy required is the lowest of the configurations. But this can shift, and we might find that some configurations using all the clients can be very fast and use a lot of energy, but maybe the algorithm and the devices are willing to pay for this. Yeah, bottom line, by looking at these values, we can get a better understanding as to how these different algorithms balance out the speed and energy efficiency, which can be interesting. Okay, so that was the first one. Second one, we will see how we can reveal efficiencies of on-device training. Okay, so for this, we are actually going to be using the Moon baseline from flower baselines and examine the training time and energy consumption per batch across 4 different models of NVIDIA Jetson devices. So these are single board computers with a GPU. And the model of the devices is here in the bottom right, with the oldest device at the bottom, the Nano, and the most recent or the most powerful device at the top. And the results show that, as expected, the fastest device is indeed, or the most powerful device is indeed the fastest in the setup. However, we actually see that it's not significantly faster than the second fastest, the Ori Nano. However, it's paying a disproportionate amount of energy to reach this small increase in training or decrease in training time. And so with this, we start wondering, how can we actually quantify whether the decrease in training time justifies this additional energy cost? And this led us to consider a common metric in digital electronics called energy delay product. And this metric multiplies the time taken to complete a task with the energy required for the task to be completed. Thus, this means that a lower EDP value indicates that a solution would be both fast and also energy efficient. And if we now use this as the metric to compare the different boards, the single boards, different boards, we see that based on this metric, the Ori Nano is the most efficient device. In other words, if we considered our subset of devices, these 4 here, if we only use the Ori Nano for this algorithm, we would minimize the time taken to train a batch for the given energy budget and vice versa. And then we started wondering how this would change if we use another algorithm. So we used FedProx, also from the flower baselines. And we saw that the general EDP rankings hold between the different devices, but surprisingly, the bottom 2 devices actually change in terms of efficiency. So it's interesting to see that the device efficiency can actually change across algorithms. And a final use of EDP can be to use it as a tool to evaluate modifications to algorithms. So you might be wondering about 2 different implementation details for your algorithm, and you can use this metric as a metric to help you determine if those adjustments that you're considering actually lead to efficiency gains. Okay. So third point, I'm going to see we can also use Collext to help us identify implementation issues. As we were comparing Moon and FedProx, so from the flower baselines, and we were looking at the round time between these 2 algorithms, we saw something that surprised us, which is that despite their similarity, we anticipated that Moon's additional forward passes would actually increase its time cost, because unlike FedProx, which only does a forward pass on this training, Moon actually completes 3 forward passes per round. However, when we look at the round times, these normalized times here, we don't see that it seems very narrow. And so this led us to think that potentially the issue is that we're not using a big enough model for these experiments. And the answer was yes, actually. But then the problem became, or the difference became too apparent, because if these are the only differences, the forward pass between the 2 approaches, now the difference is too large. So we looked at the code, and we actually saw that just one single line of code where we saw it contained the necessary GPU to CPU memory copies were enough to cause this slowdown. And once we tweaked it, we actually saw that we finally saw the performance of the Moon baseline more in line with what we expected. Okay, for the last one, we're going to talk about an example of smartphones with smartphone devices. And we did a lot of extensive experiments with smartphones that identified 2 main causes for mobile stragglers, and which are, as expected, both due to hardware heterogeneity. First, the there's compute speed differences, which can be very noticeable during model training, not as much during inference. And in the plot here, we see a CPU trace of NFL round filtered to 3 smartphones with similar CPUs. You can see when the round starts with this jump in CPU utilization, and when it drops, it's when the round or this device finished pushing its training results back to the server. And you see that even though these smartphones have similar CPUs, the blue line here is significantly slower than the other smartphones. It takes longer to go down after it went up. And this is surprising because the CPUs are similar, but if we actually look at the power consumption, this helps us understand what the issue is. Because while the other two smartphones show an increase in power consumption during training, and when they start training, the decrease when they stop, this device actually stays low for the entire duration, which means that the CPU is actually underclocked. So even though you know the CPU specifications, if you just use it without actually testing the device on a real setting, you don't know if there's actually some settings that might affect the performance of the device. Yeah, another use case very quickly is the data reception and transmission, which can vary across devices and can be very different. So here we have two devices transmitting the same model, and we see that the amount of uploaded bytes, so this is the process of transmitting one model back to the server, can vary a lot between the devices, even though they claim to have similar specifications. Okay, I'm almost done. I just wanted to mention that we wanted to deploy a lot of Flower code, different Flower code, to make sure that our system was working. And so we're very happy to use the Flower baselines as a source for this repository of third-party Flower code, so not our own code to test on the testbed. We were happy to see that most of the Flower baselines that we deployed were actually ready to go. We found some didn't work. One, for example, was because there was some decoupling that was needed between the server and the client that was shared in a simulation environment, and that was okay. But as we decoupled them in the real experiment, that was an issue. And there was another one where there was unsupported serialization, where the client was trying to send something to the server that the server couldn't support. And so this seemed to work in a simulation, but didn't work as we tried to use it on the devices. Okay, the limitations. So we have, unfortunately, our Android deployment requires some effort. You can't directly use your Python code. It supports Kotlin, and we don't support also any machine learning platform because there's no support for it in general. But we have experiments working with TensorFlow Lite, and we provide a code template that you can use to get you started and hopefully alleviate some of the issues. We also are struggling to combine experiments between Android and SPCs. For now, we have to pick one subset between these two. This issue is because of the model incompatibility as you try to combine the two different machine learning frameworks. And we don't have network emulation, but we want to support it relatively soon. Okay, I'm sorry, I went a little over time, but we are finished. I want to mention just that Collect is available to interested researchers, and we hope you find it useful. I want to mention that we wrote a paper based on this work and was accepted at the ACM IEEE Symposium on Edge Computing this year. And you have this QR code here at the bottom that you can scan to get additional details, and also a link to the paper. And yes, that's it. Thank you. We'll be taking questions.
Thank you for the super interesting talk. Now, as you were presenting this, I started to remember some of the things we discussed in the Flower Summit. Or I think we discussed, I'm not 100% sure, but yeah, I took some notes about some questions I have. So, because we are not me, but in Cambridge University group, we are trying to do something like building a cluster of devices a bit, but it's not nearly as polished as this. So this is amazing. So my first question is, in your YAML, you specify what devices are going to be exposed to the experiment, for example, right? You have a list of devices.
Yes.
Does this mean, is this exposition of devices happening at the strategy level? Like the strategy does when it does a sampling of clients, it filters them out based on some metadata, or is done much earlier? Like I'm thinking from the perspective of a standard job scheduler to other platforms like Slurm. Like, oh, in this job you only have 2 Raspberry Pis, 2 Jetson Nanos, and there's no way you're going to see the rest.
Yes, yes, the second approach. So we control the devices that the experiment sees by controlling which devices we use for the deployment.
Okay.
So we only so if you ask for 2 Jetson AGX Orins, we only deploy on the 2 AGX Orins.
Okay. So this, for example, enables 2 experiments happening at the same time, as long as there is no overlap between clients, for
Yes,
example.
yes. Yeah, theoretically, yes. We currently are working, we're still debating if we want to implement this as a solution, because given our current number of devices, it might be too small if we want to run interesting experiments, because even though we aim to have a large number of devices, we still only have 48 total devices. So assuming 2 users could share these 48 devices, I think it would be great if we could share.
I think 48 is not a small number, but I agree that some experiments do need a big number of clients. Okay, another question I wrote is the metrics that are captured at the strategy. Well, I don't know, are there metrics? So clearly there are some metrics being reported to your dashboard or being generated from the clients, but I don't know if from the strategy itself also. But my question is more, are clients streaming their own metrics, or are they being routed through the strategy, and the strategy is, for example, the only place where it's written into a CSV or is logged in your metrics
Yes.
S3 or whatever.
Yes, we're currently not going through the strategy, so we have a separate channel to send the metrics.
Okay. Interesting. I have one question about some of the results you were showing in slide 16. I think you were showing, like, I think a very interesting observation, like, even if you train for 5 times longer, then the extra accuracy you get is very small.
Yes.
Oh, wait, no, it was a different slide.
This
Yes,
one?
this one, yeah. Could you give some insights on, if you remember, like, how did you partition the data, for example? Because I guess it will be very different if it's like how fast everything, the accuracy curve plateaus. Maybe it varies between an easy FLS setup or a difficult one.
Yes.
What?
I think so. I wasn't the main person working on the experiments. It was actually Boris, who I think is not in this part, but in the participants. But we do have this information in the paper. I'm seeing if I can find it in my backup slides.
I think don't worry too much. I will take a look, but yeah. No, I think it's an interesting observation.
But it definitely to answer or part of it, the question, it definitely changes as the results that you plot here definitely change depending on the data that you're using and how you're partitioning the data, for sure.
Mhm. Okay. I think these are the main questions I had. Also, well, I like the table you showed at the end of the challenges you identified with different baselines you tested on. I think I took a screenshot. I think that's useful for me to know. Well, but now that you have identified some of the problems, like the moon problem you mentioned about the unnecessary copy, if you want to come to a small contribution, That would be one example.
Maybe that I'll start there. Yeah.
Any more questions? I'm checking if in Slack there are questions, or anyone from the audience has a question, you can write it in the chat and I will read it. But otherwise, maybe we can go for the next talk since we are a bit over time. Okay, well, thank you very much, Amandio and Janis, for this super interesting work.
Thank you.
I'll be sure to check the repo. Thank you.